Professor, can you hear me?
I can hear you.
Okay, I'm just letting you know, I just came to check in with you. I have a VA appointment today and I can't stay for class.
Okay, well, thank you for letting me know. I'll post the video after, probably later on today.
Okay, and it was just the assignments that were due yesterday, and then we have the other ones that you assigned tonight.
Yeah, so 3-1, I only asked you to do like the first two problems, I think, and then I've extended it now. 3-1 is now due on the 6th. So
Okay.
These are the only two things that'll be due.
Okay, sounds good.
Okay, all
Thank
right.
you.
Yep, have a good one.
You too.
Okay, good morning, everyone. 9 o'clock. Let's see, we got 10 people here. Let's just wait a few more minutes. Does anyone have any questions before we start?
We can continue working on homework 3.1 today, right?
Yes,
Okay.
I extended the deadline this morning, so it's now due on the 6th.
Okay, thank you.
Yeah, and I'm hoping I'm going to be able to get through both finish 3-1 and 3-2 today, and that way we'll be kind of back on track. We'll see how things go. You might notice I'm going to move a little faster today, but I think the material is easy enough that it won't like leave you confused. We'll see. Okay, all right, let's get going. So today we're going to finish 3-1, 3-2. And then Monday we'll start 3-3. Homework 3-1 and 3-2 are due on Sunday night at 11:59 p.m. Our exam is still a few weeks away. And your camera. Okay, let's get going. So we finished last class on doing this example 6 out of 3.1. And I had told you that this last one, f of x plus h, was kind of like a big deal, that this is going to be important. So let's continue this section where we were evaluating a function at different values and different plugging different things into it. One quick definition before we proceed. Whenever you're given some relationship between two variables, x and y, in some equation, there's two ways that we can represent that relationship. One is called the implicit form. Okay, implicit form. And that just means you have an equation and you've got your x and your y, and they're just mixed up in there, and whatever it looks like, and that's what we call the implicit form of the relationship. The explicit form of the same equation is when you can take that equation and somehow solve it for one of the variables. So if I take this equation, let's say 3x plus y equals 5, and I go try and solve for y, I would subtract 3x on both sides, cancel out here, I get y equals 5, take away 3x. Or you could write it the other way around, like it has up here, 3x minus 5, or minus negative 3x plus 5, sorry. Either way, we have solved for y, okay? And whenever you solve for one of the variables, that is called the explicit form, all right? So that will come into play later on when we are dealing with inverses of functions. And then also this comes into play in the calculus 1. Sometimes it's not possible to solve or to take an equation and put it in explicit form. Sometimes you can't do it. It's just like algebraically impossible to isolate one of the variables by itself. So in calculus, we have to say, okay, well, how do we deal with it when we only have that? So that's for later. We still have, this class pre-cal, then you get to Cal 1. So, All right, so those are the two forms of a relationship, the way they can be written. Now, let's just put that away. We're going to move on in this section to the next very important topic, this thing called the difference quotient. This is actually, this right here, this definition is like the heart of calculus, okay? Calculus is going to rely on your ability to understand this quotient right here. So in this class, in college algebra, all we're going to do, okay, is take this expression and make sure we understand how to algebraically manipulate it. That's it. It's just, we want to know the algebra behind this expression. In calculus, we see what we're going to do with it, all right? So here's the definition. The difference quotient, okay, the difference quotient of any function, okay? So if someone hands you a function, we can always try and find this thing called the difference quotient of that function, okay, for any function. And all it is, it's kind of like three parts. It's the top left part of this quotient meaning ratio or division here. The top left of this is what you get when you plug x plus h into the function. And then the next part of this, minus, you're going to subtract the function itself. And then when you're done doing that, you're going to divide the whole thing by h. Now, again, in this class, we are not really interested in why you would ever want to do this, all right? We just want to make sure we know how to do it. And then when you get to calculus, they'll show you, you know, oh, here we're going to be trying to do this. And it turns out that when we try and do it in calculus, we have to be able to do this algebraically. All right. So this is just so when you get to Cal 1, you're like, what difference, what? And you don't know what you're doing. We don't want to take time in calculus trying to learn this. So for any function, we can always figure out what this difference quotient is and then move on. So we're going to do some examples here. I recommend you just memorize that difference quotient, like as soon as you can. All right. Now you'll probably forget it when you get to pre-cal, but at least you will have at some point memorized it, and then you'll have to go rememorize it. All right, so here we go. We're given in this problem, this example, three different functions, right? A, B, and C. For each of those functions, we should be able to find the difference quotient. So we're going to just start with the first one, work it out, and then we'll move on to the next one. So let's start with this first function. A equals f of x, I'm sorry, A is f of x equals 2x squared minus 3x. And I want us to find the difference quotient. I'm just going to put DQ for difference quotient. All right. Now, this is where we have to remember what the difference quotient is. So I'm going to write it down over here. It's the difference quotient is f with x plus h plugged in minus just the function itself, f of x, divide the whole thing by h. All right. That's what we want to do. All right. So let's work on this function. Let's get the pieces we need. Okay, so this is going to be like scratch work. I'm going to put SW for scratch work. So here's my scratch work. First thing I'm going to do is figure out what f of x plus h is. Now that's why I was telling you last time that plugging x plus h into a function is important, because you need it for the difference quotient. So when I plug x plus h into the function, well, here's the function they're giving us, right? So I'm just going to replace the x in this with x plus h and just rewrite it. So let me do that. I'm going to have 2, I'm going to have x plus h. I'm going to take that quantity and square it, subtract from that 3 times x plus h. Now, I gave you an opportunity at the end of class last time to do that. You actually did this problem. You plugged in x plus h into an example. It was this one right here, right? I let you do that, and then I worked it out here on this page. So this is actually the same problem, isn't it? Isn't that the same problem? We did this last time, but I'm going to continue here. Hold on. I'm going to act like we didn't. I'm just going to work this out. So what we have to do here, and just pay attention to order of operations here. You have to take this and square it first, right? You've got to do that first. You got to do x plus h times x plus h, and then do your little, multiplication there. Now, I'm not going to show that work because we did it last time. I'm just going to write down what we got. We got 2, and then when you multiply all this out, you've got x squared plus 2xh's plus h squared. But very important, the 2 must distribute through to that, okay? So everything that was here that we squared here in red became this stuff in parentheses, and the 2 needs to multiply through. And then we still have, now we can distribute the -3 through. We still have -3x minus 3h. And the last thing I'm going to do is distribute the 2 through. Okay. Questions on that? No questions? We cannot combine any like terms together here, right? There's nothing we can put together. In order to combine like terms, you have to have the same variables raised to the same power, and we don't have that here, right? We don't have any of the same variables to the same power. So that's it. That's what f of x plus h is, all right? So in the difference quotient, this top left corner, right? This top left of the difference quotient will be what we just got there, all right? So that's the first part of my scratch work. Now, the second part of my scratch work, I need to know what f of x is, which is the top right, right? I need to know the top right part of this. Well, that's just always the function itself, which is easy because they gave us the function, right? So I know what f of x is. It's 2x squared minus 3x. So there's nothing for me to do there, right? There's nothing for me to do. That's going to be the top right of this difference quotient. And then what I'm going to do is I'm going to take the whole thing and divide it by h, right? That's what I'm going to do. So here we go. I'm ready to write the difference quotient. So if I take this, the difference quotient for that function is the top left of this, which we just said was 2x squared plus 4xh plus 2h squared minus 3x minus 3h, right? That's my top left. And then very, very important, and you have to be careful here, we are going to subtract, right? We are going to subtract the function f. So when we subtract, I put subtract, and then I put the function f, but I must put that in parentheses because that negative sign must distribute. That's where a lot of students make the mistake. They forget to put the parentheses around f of x. Take the whole thing and divide it by h. Okay, so I'll just clarify this again. The top left of the difference quotient in yellow there is all of this. The top right of the difference quotient is this. And then of course the bottom is just h, and that will always be h. Every time you do difference quotient, the bottom will always be h. Is this clear? Okay, what we're gonna do now is we're gonna simplify this, all right? We're gonna see if we can simplify it. Now, if you do it right, okay, if you do it right, and don't make any mistakes, the h on the bottom will always cancel. You hear me? If you do it right, and you do your algebra right, at the end of this, the h should cancel. Let's see. And that goes for all of these, no matter what, this should happen. Okay, so I got 2x squared plus 4xh plus 2h squared minus 3x minus 3h. Now distribute this through. So we get minus 2x squared plus 3x. The whole thing divided by h. I realize that it's you know, it looks like a complete disaster over here, you know, but good things are about to happen. Good things are about to happen. You should see here that this 2x squared cancels with the minus 2x squared, and that the negative 3x cancels with the positive 3x. So now that those have canceled, I'm going to rewrite what I have. 4xh plus 2h squared minus 3h. That's all I have left on top. And on the bottom, I have h. Now, at this point, you should notice that in the numerator, every term has an h in it, right? There's an h here, there's an h, well, there's actually two factors of h here, and there's an h here. So since the numerator, every term has at least one h, I can pull a greatest common factor of h out of the top. So I'm pulling one factor of h from each of these. And at this point, I can now see that the h can be canceled. And that leaves me with just what was in parentheses, 4x plus 2h minus 3. And that's my answer. Now, again, right now, you have no idea what this does, okay? You have no idea what this does. So I'll just give you a real quick glimpse into what it does, okay? So I'm gonna just real quick peek into Cal 1 and see what we would use this for. What we do in Cal 1 is once we get to this part, okay, when we're in Cal 1, what we're gonna do when we get to this part is we're gonna let h basically become 0. Now, don't ask me why, okay? So we let h be 0. If we let h be 0, what do we get here? This 2h goes away, right? And all you're left with is 4x plus 3, right? Or sorry, minus 3. Got it? Understand? That's now, again, you still have no idea what I'm doing. So we've got our original function is 2x squared minus 3x, and we've got this answer 4x minus 3. Let me show you now what that allows us to do. So I'm going to go to some graphing utility. And the original function, I'm going to graph it, 2x squared minus 3x. 2x squared minus 3x. Okay, so here's a function, right? Here's a function. In calculus, here's what we're trying to do. In calculus, we say, okay, here's a function. If I go to some random point on this graph, like let me go to this point right here. That's the x value of 2, right? So if I plug 2 into that function, it happens to spit out 2, right? So that's like the point 2, 2, right? Okay. In calculus, what we do is this. We say, can we figure out the slope of a line? Okay, think about a line, right? All lines have slopes to them. Can you figure out the slope of the line that goes through that point, but is like tangent to this graph? Okay, can we find out the slope? Now let me just show it to you first. Let me just think real quick. There it is. Okay, so there is the line. There is the line. That blue line goes through that graph at one point. Y'all see that? And it's like kind of tangent to that graph. It's like balanced on that graph. With me? What's the slope of that line? Shit, I don't know, right? You look at it, you're like, I don't know what the slope of that line is. Well, guess what? Remember how we found that answer just a second ago? We got 4x minus 3, right? We got that answer and we're like, what is that? You know, that's from the difference quotient. What we do here is we take the 2 and we plug 2 into this. So if I plug 2 and I get 4 times 2 minus 3, that's 8, take away 3, that's 5. And here's what I can tell you, the slope of that line is 5. That's what the slope of that line is, all right? Guarantee. And I can do that now for any point on this graph. So let me go to a different point. Let me go to this point right here. Again, there's some line that goes through here, okay, that's running through here, kind of tangent balancing on that. What's the slope of that one? Well, I'd have to go to the point, the x value, this is -1/2, and I would have to plug that into that formula of 4x minus 3. And so if I plug -1/2 in there, let's see, 4 times -1/2 is -2. And then take away 3, we get -5. So I can tell you right now, the slope of that line is -5. So I'm actually going to come over here and I'm going to graph it. So there's a line with -5 as a slope. Let me see. Let me clear this out of here. So it's this line right there. You can kind of see it right there. Okay. Now, what is it? What is that? What's the usefulness of that in Cal 1? Well, this is what we call the instantaneous rate of change of the function. So we're trying to figure out, like, at different parts of the function, is the function going up or is it going down, right? That's what we're going to be able to determine in Cal 1. All right, I can keep talking about this for hours, so I'm going to stop. You just need to understand that this is very useful to us, okay, in calculus. But we are just making, this is the part we want to make sure that before you get to calculus, you know how to do all of this, okay? That you know how to do difference quotients for different types of functions. The first function I gave you was a nice polynomial, right? It's a nice polynomial function. You just plug in, x plus h. It's not that bad. Let's see the next one. Let's see if this one is harder. Are there any questions? So here's the new function, right? New function. And so we want to find the difference quotient. All right, so I'm just going to remind us over here again, the difference quotient is f of x plus h minus f of x, the whole thing divided by h. Okay, I need to do some scratch work. First thing I need to do is I need to figure out what f of x plus h is. So if I look at my original function, replace the x over there in yellow with x plus h, all I get here is 4 over x plus h. Not so bad, huh? I mean, let's plug it in. Not much we can do with that, right? Just leave it like that. Now I need to know what f of x is. This is the top right corner. Well, we know that's just 4 over x. All right, so I've got my top left, I've got my top right, and now I'm ready to write the difference quotient down. So my difference quotient will be the top left, f of x plus h, which is this piece, 4 over x plus h. Then subtract from that f of x, which we know is 4 over x. And then you take the whole thing, the entire thing, and divide by h. Are there any questions on that setup of the difference quotient? Like how I got that algebraically? I'm not calling on people because I'm trying to get us through 3.2 today, so I'm kind of going faster today. Now, I just told you that if you do this right, the h should cancel, okay? But if you go back and look at the problem we just did, the h canceled right here at this very last step. When we were here, we had h's in all the terms on top and we factored an h out, and that's what allowed us to cancel it. So when we look at where we are now with this, there's no way we can cancel this h. Like you can't just cancel this h and this h, right? I mean, that h, this h right here is like trapped. It's in the denominator next to a plus x. There's no simple cancellation here. So we've got to do some algebra now to get hopefully that h to cancel. All right. The question is what algebra? So this is what I tell my calculus students. I remind them of this. When you have something like this, we call this a complex fraction because it's fractions within other fractions, right? It's like you got a fraction here, you got a fraction here, you got a big fraction here. It's a complex fraction. Whenever you have this, my recommendation is to try and combine these two together into a single fraction. All right. So I'm going to go back and do more scratch work over here. I'm going to try and combine 4 over x plus h minus 4 over x. And to do that, I need a common denominator. Sound familiar? I need a common denominator. So I must multiply the first fraction by x over x, because that's what the other denominator has. right? And then over here, I'm missing the entire x plus h, so I have to multiply by x plus h over x plus h. Now, when I do this and multiply, I go straight across. I'll get 4x on top. I'll get x times x plus h on the bottom. Now, I could multiply. I could, if I want, distribute this x through, but I'm not going to. I'm just going to leave it as x times x plus h. And then minus over here, I multiply across the top. Watch what I do here. Multiply that 4 through, 4x plus 4h over that common denominator. And now I'm going to put these two together because they have the same denominator. So it'll be 4x minus, now again, you have to be super careful here because you're subtracting this numerator, which means you have to put the entire numerator in parentheses. Then that's over x times x plus h. Still working. Okay, I've got 4x. Now I'm going to distribute the negative through. Minus 4x minus 4h all over x times x plus h. And do y'all see what happens here? Y'all see these 4x's are going to cancel? So all I'm left with is negative 4h over x times x plus h. Okay. So everything I took this in green and I put them together, and when I was done with all this work, this is what I got, right? So I'm going to go back to this now, and I'm going to say this is equal to what I got here, negative 4h over x times x plus h. All of this, the whole thing over h. Questions? Now, y'all seem like y'all are following. I mean, at least you looks like y'all are paying attention. The question is, can I cancel these h's now? Do you see the h's? Do you see? Can I cancel this? So you might be wondering, like, you're confused. Can I? I don't know. Well, look, just watch this. If you agree with this, that this is really like this fraction over h, but h could be looked at as a fraction, h over 1, then you have a fraction over a fraction, right? And whenever you have a fraction divided by a fraction, it's the same as multiplication of the reciprocal. In other words, this is the same as taking negative 4h over x times x plus h. And instead of dividing it by this h plus 1, you multiply it by the reciprocal, 1 over h. And I think if you do that, it's easier for most students to see, yes, in fact, those h's would cancel. And now you are left with what was on top, which is just negative 4. And on the bottom, you're left with x times x plus h. You know you're done when the h cancels. Like that's when you know, like, okay, I reached the end. And that's your result. Questions or comments? What do you think gets hard with the difference quotient? I mean, what do you think is the difficult part of it? I mean, plugging in x plus h and plugging in x, I mean, that to me is like, okay, just plug in, fine, great. That's not that big of a deal. It's the algebra required to get the h to cancel. That's the part that's hard. In this problem, you can start to see the complexity of things because we had to put these two fractions together, and then we had to realize this was like, you know, flipped up and the h's cancel. So as you might imagine in calculus class, the hard part is not the difference quotient, like not the formula. It's the actual algebra getting the h to go away, because things get really complicated. The functions get really complicated. Let's see what our third one is. Yeah, our third one is, this one's, yeah, it's classic problem here. Okay, so this one here. All right, so here's what I'm gonna do. First thing, I want the difference quotient, right? I want the difference quotient here. So the formula is f of x plus h minus f of x, the whole thing divided by h. Okay, so I'm gonna do my little scratch work over here. I'm going to first figure out what's f of x plus h. Well, what am I trying to say? This is what happens when I plug x plus h in right there for x. So this becomes square root of x plus h. And please, please do not turn this into this. You are not allowed to split a square root apart like that if there's addition inside. You can't do it. You can only do it with multiplication, right? So if this was times, then you could say this times this. But if it's added, you can't do it, all right? So we have to leave that exactly the way it is. There's nothing we can do with that. And then f of x is just f of x. So, or sorry, f of x just square root of x. So there's nothing we can do with that. So I think I'm ready for the difference quotient. It will be equal to the f of x plus h, which is square root of x plus h, minus now f of x, which is just the square root of x, and then over h. Questions? So this is where that's so important that you understand that this over here was not equal to the square root of x plus the square root of h, okay? Because let's say you thought that's what it was, okay? Let's just say you did. If you thought it was this, then our difference quotient would actually turn out to square root of x plus square root of h minus, so subtracting out f of x, square root of x all over h, and then these things would cancel and you'd be happy. But that's not correct algebra, all right? It's not correct. So we cannot split this apart. There's nothing we can do here. There's absolutely nothing we can do to free this h from this square root, okay? It is trapped in here, so we can't cancel it. So we're stuck. You all agree? We're kind of stuck at this point. So we're going to do something crazy. Well, it's not crazy, but it's not something you would normally just think to do, all right? But it's going to work, all right? And then what happens is, again, in calculus, you're like, okay, I know whenever I see something like this, I remember I can do this thing, all right? So I'm going to take this expression, and because I see square roots, okay, this is only because I see square roots in here, I'm going to take this expression and I'm going to multiply it by 1. And we know that multiplying by 1 doesn't change anything, right? Anything multiplied times 1 is itself. But the one that I pick, the one that I actually pick is going to be extremely clever. Here's what I'm going to do. So 1 can be written many ways. One way I could write 1, anything over itself is 1, right? So watch what I put here. I'm going to put the square root of x plus h plus the square root of x. And then I'm going to do the same thing on the bottom, square root of x plus h plus the square root of x. So you have to agree with me that everything in blue here is the number 1, right? Isn't that the number 1? It's just really a weird way of writing the number 1. And the reason I chose this is because what I did is I looked at what's here. Okay, I looked at what's here and I took its conjugate. Okay, so this here on the top here, that is called the conjugate. The conjugate, right? So if you take this, its conjugate is that. So it's basically the exact same expression, but what we do is we change the sign in the middle of them. So instead of having a minus, we put a plus here. Okay, Remember, our goal is to get the h to cancel. Now, you might be saying, to go, why in the hell are you doing that, right? Like, this is crazy. Why would you do that? Well, let me show you. I'm going to show you why I did it. Over here, I'm going to do my scratch work. I'm going to take the square root of x plus h minus the square root of x. That's this one up here. And I'm going to multiply it times that conjugate that I just did on top. Right? Because that's how we multiply fractions. We multiply straight across. Right? So I'm going to multiply these two together. That's what I'm doing, just straight across here. So let's talk about what happens here. This times this is the square root of x plus h times itself, right? Times itself, which is the same as squaring it. That's my first multiplication. Yeah? And when you square a square root, it's going to go away. It's going to kill the square root off, but I'll do that on the next line. Okay, and now let me do the second multiplication here to here. All right, so I'm taking the square root of x plus h and I'm multiplying it times positive square root of x. That turns out to be a positive square root of x plus h times the square root of x, whatever that is. And then this is where the things get good. Look at the middle multiplication, this middle one. You're doing negative root x times square root of x plus h, which gives you a negative square root of x times square root of x plus h. And do y'all see what's going to happen here in the middle? Do you all see that this right here and this right here are exactly the same things? Just they're written in a different order. And do you see that one of them is negative and the other one is positive? And so what's going to happen to them? Cancel out, right? They will cancel. And that will always happen with the conjugate. Your middle two will always cancel. Anytime you multiply something by its conjugate, the middle two terms will guaranteed go away, which is why I use the conjugate. Now, I'm still not done. I need to multiply the last multiplication. I do this one times this one. So I have a negative times a positive, which gives me negative. And then I'm doing root x times root x, which is root x squared. And so the middle terms are gone. We already said that. We said the first term, when you square the square root goes away, you get x plus h. And then at the very back, you're going to have minus. And then here is just going to be x because you square the square root again. So the square root goes away. And how about that? The x's go away now. And you just get h. Wow, okay. So all of that stuff on the top multiplied together gives you h. So let me rewrite. This is equal to h over now on the bottom I have h times this. I am not going to multiply that through. I'm going to leave the h outside. I mean, I could multiply the h through to both of these and just stick the h in front, but I'm not going to do it because remember the whole goal is to get that h to cancel. So I'm leaving the h out here. And now I see that this cancels. This becomes a 1. Be careful. That's gone. So your final result is 1 over square root of x plus h plus the square root of x. And that's it. So I'm launching a poll. I just want you to give me kind of a yes or no in terms of like, are you getting the idea here for the difference quotient as far as what you are doing to set it up and what the goal is? Okay, good. So like I said, the part that makes this hard is the algebra within this is what gets tricky. All right, it's the algebra. So you have to do a lot of these problems to get comfortable with them. And in calculus, you will definitely be indoctrinated, is that the right word? Into calculus, but they will baptize you with the difference quotient. All right, they will. That's what's going to separate the people who do well from the people who don't do well, or the people who can do the difference quotient and get that H to go away. So all these different algebra kind of tricks and skills are going to come into play. Here, the main skill here was the conjugate. The conjugate is what made this happen. And I do that, you do that when you see square roots, you think conjugate. On the previous problem, complex fraction, right? Fractions within fractions. What's the trick there? Get a common denominator, put them together, right? Now, the one before that wasn't really tricky. It was just figure out what these are, plug everything in, things canceled. We didn't have to do anything tricky here. It was just the algebra is pretty clean. Did you all agree? Clean algebra versus common denominator, a little trickier. And then this conjugate is really crazy. Now, I'm going to offer one to you as a bonus, okay? And this is the last thing I'm going to say about this problem because I want you to turn it in with the exam. So when we take our exam on the 20th or 21st or whatever it is, when you send me your work, right, you're going to get all your work sent to me as a single file. Your last page, put bonus, put today's date on it, and just include it, all right? What I want you to do is the difference quotient for this. All right, so the function is 3 over the square root of x. Now, this is not like a super hard problem, but I haven't shown you how to do this yet, okay? But I'm telling you, I've shown you enough to do it. If you're willing to kind of like try a few different things, it will work. All right, you just have to be willing to try. So I want you to find the difference quotient for this. And that's going to be due the day of the final, or day of exam 1. And just make sure you put on it your name and then put today's date, which is 2/2/2022. Now, look, I realize you can all go probably find this somewhere online or find a friend who knows how to do this. Really, this is about, can you figure this out? Okay. Can you figure this out? Put as much effort as you can into it. I think everyone in this class can do this. If you can follow me on those last 2 problems, you're capable of doing this. You just need to work at it. Okay, that's it. Any questions on that? Difference quotient, we're done. 3 examples is not enough to feel like you're good at difference quotient, but that we have to move on. So the next topic here we want to talk about is finding the domain of a function. So we talked a little bit about domain last class. Basically, the domain of a function is the stuff that you can, C-A-N, that you can plug into the function. That's the domain. It's like we talked about the car wash, right? Certain cars can go through the car wash, you know, a truck that's too big can't. So here, when we're talking about domain, we're saying, can you tell me what values of x are allowed into these functions? So let's start with A. For this function, f of x equals x squared plus 5x. And I should probably start with this. Right now, where you are in your math life in terms of functions, there's really only 2 things that you ever have to be worried about. Okay, there's only 2 things right now that you have to worry about when it comes to functions. The 2 things you need to worry about, 2 issues, we'll say, that you have right now are: 1, you can't divide by 0, right? You can never have division by 0. So you always have to be paying attention to your function, that you never plug something in that's going to cause division by 0. The other issue you can't do is on a root, if this number out here is an even number, like the square root or 4th root or 6th root, If it's an even root, then this in here, right here, has to be greater than or equal to 0. Whatever's underneath this must stay non-negative, because we can't take square roots of negative numbers. Those are the only two issues a college algebra student has to worry about. Now, when you get to pre-cal, there's a whole new set of functions that you have to worry about. Actually, you know what? Later on, we're going to do logarithms, and then there are going to be issues with domains with logarithms. But right now, at where we are here, this is the only two things we have to worry about. So when we look at A, if I start to ask you, are there any values of X you cannot plug in? You start thinking about numbers, right? You start plugging numbers in here for X. There's no way you're ever going to get this to have one of these two issues. Like, you can never have it divide by 0, because there's no division here, right? There's no division. So you don't ever have to worry about division by 0. And there's no even roots here. So you don't ever have to worry about, keeping something positive or non-negative underneath. So there are no issues here. Agreed? This has no restriction. This is a car wash that can take any car you ever want, truck, 18-wheeler, whatever. It can wash anything, right? That's what we have. So how do we represent that domain, the answer? There's a couple of ways to do it. You may have seen this before. All real numbers is one way you could write it. In other words, you can plug any number you want into there. That's one way that you could do it. Another way you could write that answer, and the way that the computer wants you to write it or put it in as your answer, is they want you to use what's called interval notation. So they want you to put negative infinity, comma, to infinity. And that just means you can pick any number between negative infinity and infinity, which means any number. And then there's another notation that we can use, and it's a capital double struck R. That double struck R means all real numbers. So all three of those answers are the same. There's another notation called set notation that would go like this. The set of X such that X is bigger than negative infinity, smaller than infinity. Now, if you haven't seen that before, it's okay. Don't worry too much about it. This is called set notation. This is called interval notation. Interval set. All right, let's move on to B. Try and squeeze B in here. B is the function g of x equals 3x over x squared minus 4. All right, let's see. Annika, are you here?
Yes.
Okay. So Annika, looking at this function g, are there any values of x that you think we have to avoid here that would cause an issue?
Maybe like +4 at the bottom.
If this, yeah, so if this becomes a +4, right, then we have a trouble, because +4 would give us 4 minus 4, yes?
Yeah.
So we have division, right? So since we have division, we have to look and ask ourselves, when is this equal to 0? I don't want that, right? I don't want this to be equal to 0. So I'm going to ask myself, when is it 0? And so there's a few ways to solve this, right? We have a couple of different methods to solve this. We could visually do it, but we could also do like a difference of squares. Set each of those equal to 0 and get -2 and +2 as our two answers, right? So there are two values of x that cause division by 0. If you try and plug in 2, you'll get 0 here. If you try and plug in -2, you'll get 0. What about 0? Can we plug 0 in? Can you plug 0 into this function? I'm seeing Alyssa say yes. Yeah, we can plug it in because 3 times 0 on top would be 0. And on the bottom, 0 take away 4 would be -4. So you get 0 over -4. Well, that's just 0, right? It's not a problem. Some students will say, you know, oh, you can't plug 0 in either. Well, you can't. So the only two issues are these two. So the question is, how do we write the domain? I'm going to do interval notation. I want all numbers except for these two. So here's the way I like to think about it. If you do a number line, this number 2 and the number -2 are not allowed. So I'm going to put open circles here. But you are allowed to have anything to the left of -2, anything between -2 and 2, and anything to the right of 2. That's kind of a visual representation of our answers. So the way we write this in interval notation is we look at first everything over here. That would be everything from -infinity all the way to -2. And then whenever we're doing interval notation, we use a parenthesis next to the number if we do not want to include it. So I don't want to plug in -2 here, right? -2 is not allowed. So I put a parenthesis next to the -2. Then I'm going to do the next piece, which is the stuff in between -2 and 2. So I put -2, comma 2. Again, parentheses on both of those because I do not want to include -2. I do not want to include +2. And then I want everything to the right of 2, so 2, comma infinity. Again, do not want to include +2. And then the last thing we do is we put this big U between these, and that's called the union symbol. So all we're doing is saying any number between here and here, and anything between here and here, and anything between here and here. It's easier, set notation is actually easier for this, because if you did set notation, it would look like this. The set of X such that X is not equal to 2 and X is not equal to -2. So instead of telling me what it can be, in set notation, you can just tell me what it can't be. It's much easier. But, you know, whatever, we're going to stick with the interval notation. Let's look at part C here. So that was that one. This is this one. So for C, we have the function h of t. We're using the variable t instead of x. Square root of 4 minus 3t. So let's see. Michael, is Michael here? Michael Guerrero?
Yeah, I'm here.
Okay, how's it going, Michael?
Good.
Good. So looking at this function h, any issues you see?
Square root.
Yeah, and what, you cannot have what underneath that square root? You cannot have a what? Can't take the square root of what?
Positive or negative?
Negative. You can't take square root of negative, right? So here's what we're going to do. We're going to ask ourselves, right, Michael, we're going to ask ourselves, hey, we need to make sure that 4 minus 3t, we need to make sure that it's never negative, right? It's never negative. So we want to know, when is it bigger than or equal to 0, right? That would tell us what values of t are good, right? Whenever that's greater than or equal to 0. So how do we solve this thing? This is called a linear inequality. Linear inequality. So to solve a linear inequality, we just treat it almost like a linear equation. We just move things around. So I'm going to move the 3t to the other side, make it positive 3t. So add 3t to both sides. And then I will divide by 3. And I get that. T has to be less than or equal to 4/3. So again, on a number line, if I go to 4/3, what we're saying is that the value that you're plugging in must be smaller than or equal to 4/3. That means 4/3, it can be 4/3, and everything smaller, so everything to the left forever. The way we write that in interval notation, negative infinity, it's almost like we're reading this left to right, okay? Negative infinity is way out here, comma, and then we want to get to 4/3, and we want to include 4/3, right? We want it included this time. So I will put a bracket on the 4/3 instead of a parenthesis. That's it. That's our domain. All right, last one. I'm going to give you 4 minutes to see what you come up with for this one. All right. Now this one's weird because there's kind of like multiple issues. We have multiple things happening that we have to be careful with. So see what you can do in about 5 minutes. And just to warn you, I'm going to call on Araceli, or Gloria, or Michelle. I'm calling on people who weren't here, I think, last time, or at least didn't respond last time. I know it hasn't quite been 5 minutes, but Araceli, do you have anything yet that you can provide us with, what you're thinking here?
What I did for the radical, I just repeated from the last step,
Okay.
but then
So
I
you-
kind of got stuck on that part. I'm not sure. if I
So
did
you
it right.
took 3x plus 12 and did what with it?
I did is it the greater and equal
Yep.
to 0?
Yep, greater than or equal to 0. Okay, good.
And
Now-
then I just,
Yeah. Solve. Did
And
you
then I
solve for
just-
x?
yes,
Okay, so you subtracted 12 on both sides?
yes.
Okay, and then divided by 3.
Yes.
Okay, so x is bigger than or equal to negative 12. Yes?
No.
No? I mean, I said 12, sorry. X is greater than or equal to negative 4. Sorry.
Yeah.
Yeah, okay. I wrote it and I said something different. Okay, so you got that, yes? Everyone
Yeah.
good with that? So that's the first condition we have. X must be greater than or equal to negative 4. Now, the other condition, Michelle, did you look at the other condition? Is there something else that would cause a problem in this, Michelle? You're on mute. I can't hear you.
Oh, sorry.
It's okay.
The negative 5.
Okay, so we can't, this
Okay.
cannot be 0, right?
Mhm.
So this can't be 0. So let's see, this right here, we don't want this to be 0. So let's figure out when it is, right? So all we have to do here is add 5.
Yes.
So X basically can't be 5. So we have two things happening here. X must be greater than or equal to negative 4, and at the same time, X can't be 5. So what I would do is I would draw a number line. I would put negative 4 here, and I would put 5 here. And then I'd say to myself, okay, X can't be 5. We already know that. So I'm going to take 5 out of here, right? No 5. X has to be bigger than or equal to negative 4, which means to the right of negative 4. But we can't be 5, but we can be bigger than 5 forever this way. And we are allowed to be negative 4. It is okay if it's negative 4 because we are greater than or equal to. But that's it. It's just the stuff between here and here, and then the stuff from 5 on. So I would write that negative 4 comma 5, a bracket on the negative 4 because I want to include it, and then a parenthesis on the 5 because I don't want to include it, and then union, and now this interval is everything past 5. So 5 off to infinity, parenthesis on the 5 because I don't want to include 5. So this little union with the 5s like this is almost like you're jumping over 5. Right? It's like, okay, I'm gonna start negative 4. I can be negative 4. I'm gonna go all the way up to 5, jump over 5, and then from 5 go on forever. That's what that notation means. Okay, questions here? I have a side question for you. I'll give you two problems to look at. If I give you 4x is greater than 12, and I give you negative 4x is greater than 12, when we solve these, if I solve this, I divide both sides by 4, right? Divide by 4, and I get x is bigger than 3, and that is correct. Over here, to get x by itself, I'd have to divide by what? Negative 4, right, instead? And there's something that you have to remember about inequalities. If you multiply or divide both sides by a negative, what do you have to do to the inequality?
So you have to flip it.
You have to flip it. Okay, so if we divide this by negative 4 here to negative 4, you have to remember now that that's going to flip. So it becomes x less than negative 3. Inequalities work that way. Anytime you multiply or divide by a negative, you flip it. It has to do with the fact that a negative times a positive is negative, and that a negative times a negative is positive. It has to do with that. That's why you have to flip it. So, okay, I just want to remind you of that, and we're going to move on. Okay, the next and last topic for this is to understand what these four notations mean. Okay, so if you are given two functions, right? Say you're given an f function and then you're given a g function. If you're handed two different functions, these symbols represent how you can operate with those functions. You can either add them together. That's the first, right? The first one, this is, you're going to add them. This is, you're going to subtract them. This is multiplication. And of course, this is division, right? So it's the 4 arithmetic operations between 2 functions. So let me show you how to do these for part A. If I want to know what f plus g of x is, all I'm going to do is take the f function and add the g function to it. So that means I'm going to take 1 over x plus 2, that's the f function, and add to it x over x minus 1. That's the 2 added together. Now, we could get a common denominator, right? We could put those together. We could, right? We could get a common denominator and force those 2 fractions together. Before I do that, I want to put here the domain. X cannot be -2. X cannot be 1. Do we agree with that? Do we agree with that? This can't happen because if I plug in -2, this one's going to have division by 0. If I plug in 1, this one's going to have division by 0. So I'd have to eliminate those. In this problem, it asks for the domain. So that's why I'm stating it here. I'm not going to combine these together. I'm just going to let that be for you as an exercise. I'll just tell you what you would do here. You do x minus 1 on top and bottom here. Do x plus 2 on top and bottom here. And multiply everything out. And then put them together into 1 fraction. For part B, the only difference between part B and A is that you have a subtraction symbol between the 2 functions instead of addition. So it would be 1 over x plus 2 minus x over x minus 1. You would actually have the same domain because you can't plug in -2 or 1. And then you could put those together if you wanted to into a single fraction. For part C, I have multiplication. F times g of x. That means you're going to take the f function and multiply the g function, which would mean you take 1 over x plus 2 and multiply it this time times x over x minus 1. And this is actually easy for us to do because multiplication of fractions just goes straight across. You don't need a common denominator. So I can multiply the top across and get x. And on the bottom, I can leave these separated, or I could FOIL this out. It wouldn't matter. You could do it either way. I'm going to FOIL it. So that's what I would get if I FOILed this. And the domain of this one is still this, because you can't plug in -2 or 1 because you get division by 0. Domain, right? This one's domain. Any questions there? Let's look at the last one. The last one's a little tricky. F divided by G. So for D, if I take F divided by G of X, that means you're going to take the F function divided by the G function, which means you take 1 over X plus 2 and divide it by X over X minus 1. Right? Now, this is the same as 1 over x plus 2, right? 1 over x plus 2 times x minus 1 over x. So what I'm doing is I'm taking a fraction, dividing it by another fraction, and that's the same as multiplication of the reciprocal. And if I multiply straight across, I get this. I have a tricky question for you here. What is the domain of this function? Tell me what X can't be. X can't be what? What do you think? Can't be, sorry. What do y'all think?
Is it this?
Is it what? Sorry, Henry, I didn't hear that.
Oh, is it the same? X can't be -2 or X can't be 1?
-1, -2 or 1. Okay, so if we look at this last one, right, Henry, if we look at this, do you agree that we can't plug -2 in here? Because we would get division by 0 there, right? So X can't be -2. I think we could agree on that. Yes? How about this though? We don't want this to be 0 either, do we? Right, because if this is
Right.
0, we have division by 0. So X can also not be what? 0, right? It can't be 0, right? If X is 0, we have division by 0. The question is 1 though. Can we let X be 1? This is tricky. Can X be 1? What do you think?
I guess it could be, right?
It could be over here, couldn't it? Like over here, it's okay to plug 1 in. Wouldn't it be okay to plug 1 in here? We get 0
Yeah.
on top, right? We get 0 on top. And then what would happen is we would plug 1 in here, we get 3. We plug 1 in here, we get 1. This would be 0 over some number. You know, it's not division by 0. Do you all agree? So it looks like we can plug in 1. It looks like we can, right? You can't. You can't. Here's why, okay? Here's why. You have to look at these as 2 separate car washes, all right? So the first thing you have to say is, okay, what can you not plug into F? Well, go back up and look at F. You can't plug what into F? -2, right? So you cannot plug in -2. Then you have to look at the other car wash, which is the G. And you say, okay, what can you not plug into G? 1, right? I can't plug 1 in here. So you have to say, oh, X is not equal to 1, can't be equal to 1. But then there's one additional thing. You put the 2 car washes together, and when you put the 2 car washes together, you have to look at this and see if there's any problems, which there is. There's a problem at 0. Here's a way to think of it. Here's a way to think of it. Let's act like just because if this were a classroom, I'd split the class in half, and I'd say half of y'all are the F half the class of the G function. But I'll just do it this way. Diego, you're F, okay? Diego is the F function, and Henry, you are the G function, okay? So Diego, can I hand you -2?
No, sir.
No. Henry, can I hand you -2?
Yes.
Yes. Okay, so that's not a problem, right? That's not a problem. Diego can't handle -2. Henry can, but so that means -2 is off the table. Now, how about 1? Diego, can I hand you 1?
Yes.
Yes, no problems. Henry, can I hand you 1?
No.
No, I can't, right? So 1's off the table. All right, now let's talk about 0. All right. Diego, can I hand you 0?
Yes, sir.
Okay. Henry, can I hand you 0?
No.
Well,
Or
plug 0
yes.
and what would you get? 0 over -1. What's that answer?
It's -1.
0 over
Or
-1,
0.
which is just 0, right?
Not just 0.
So
So
I
no.
can hand both of y'all 0, right? I can hand both of y'all 0. Agreed? And you can handle 0. The problem comes in the next step. I want y'all to now do this. I want Diego to give me his answer when I plugged in 0, right? So Diego gives me his answer, and I'm going to divide it by your answer, Henry. But your answer was 0. So I'm trying to divide by 0, which isn't allowed. Okay, so when you put functions together with it like this, you have to be real careful. You always have to maintain the domain of the original functions has to be maintained. Like if, you know, this f can't handle -2, this g can't handle 1. Okay, those are definitely thrown out. But then you have to think about what would make Henry's 0, right? What makes Henry 0? Because I'm dividing by Henry's function. So I got to make sure that that's never 0. Does that make sense, everyone? That's kind of where you
That
pick
makes
up this. You pick this up right here. That's where we pick it up. So we actually have can't be 1. There's 3 things it can't be. Okay, that's it for this section. We got to move on. So that should be enough to help you get through the homework. I'm going to also throw something in here. In your homework, you will notice that like the last problem or two will usually be something that I didn't cover explicitly in class. That's intentional. They're usually problems that are just like an extension of the ideas to see if you can kind of make it make sense. Don't look at them as bonus problems, but they're more like challenge problems. So if you see something in your homework, you're like, what the hell? We didn't talk about this. I know, okay? So I'm aware of that. So ask questions if you have them. All right, we are moving on. 3.2, the graph of a function. So this section should go pretty quickly. Let's see how it goes. So we talked about already last class that when we talk about functions visually, there's an easy way to determine whether or not the graph of something is a function or not, a function of x. And it's this thing called the vertical line test. So I have right here 4 graphs. And what I want to know is whether or not they are functions. So when we look at the first graph, as I start to draw vertical lines, I only ever hit the graph 1 time. And because of that, because I only hit once, this is a function. I know most of you are comfortable with this, so function, yes. Next one, same thing. As I draw vertical lines, I never hit more than once. So this is a function. Okay. On the next one, though, when I start drawing vertical lines, I'm hitting it more than one spot. And so this would not be a function. And same with this one. I hit it more than once, not a function. Now, most students are comfortable with this, right? Vertical line test. The thing that you need to remember is later on in this class, we are going to be drawing functions by hand. It's going to be pretty complicated because we're going to have to do all these different things to draw these things and get them as accurate as we can. When you're done drawing, you need to always remember when you're done with your picture, you always need to remember to just look and make sure the vertical line test passes. Because it would be wrong if you drew me something and then it failed the vertical line test. It would no longer be a function. So make sure you're always keeping that in the back of your mind when we are talking about functions. Okay, that's functions, the vertical line test. Now, the next part of this is a test to see whether or not you understand what it is that a function gives us in terms of what information is contained within a function. So we have to remember that anytime you're looking at a graph, this is a function, right? This passed the vertical line test, right? So that is a function. When we're looking at a function, every point, every single point on that graph has what we would consider to be the x coordinate and the y coordinate. This is the input, this is the output, right? So it's like this is the x and this is the function's value at that x. So let's start with the first thing. What are f of 0? So f of 0 means what happens when I plug 0 into this function, when I plug this in for x. So that means I'm going to look at my graph, I'm going to go to the x-axis, I'm going to go to 0, which is here, 0, right? I'm looking right here. And I'm just going to look up and down for a point, right? I just look up and down and I see a point up here. It's the point 0,4. So when I plug this in for x, this is what comes out. So the answer to that is that f of 0 is 4, right? You plug in 0, it spits out 4. The next one is, what does the function spit out when you plug in 3 pi over 2? So let's see here. Is it Malak or is it Malak? Am I saying that wrong? Malak? No Malak? Sierra?
I have a question.
Yes, go.
Why would you plug it in? Like, why would you plug it in for X and not for Y?
Okay, so maybe I can illustrate this way. Let's go look at a different function for a second. Let's say I gave you this, okay? How would I let you know, Lizette, that I wanted you to plug in the number 2? That if I wanted you to replace X with 2, wouldn't I write
Oh.
this? I would write f of 2 like that. And that would tell you, go replace the X with 2 and tell me what you get. Yes? Same thing. This is like the X. This is like the X. This is like the X. Make sense?
Yes, thank
Okay.
you.
Good. Thank you for asking the question. Sierra? No? Sierra? I don't see Sierra. Okay. How about Miguel? Miguel?
Hello?
Yep, I can hear you. I'm looking for you though. Where the heck are you? Miguel, yes, you hear me?
Yeah.
Okay, can you tell me what the function's value is at 3 pi over 2?
Well, does it not go through the line?
What do you mean?
Am I looking at the second point through X?
You're looking at, so this is the X value. So you're looking at where the X is 3 pi over 2, and you're just telling me what the Y value is here, right?
So would it be 0?
0. Okay, good.
All right.
0. That's it. Okay, Miguel, how about the next one? Just to make sure you understand it. Now go to 3 pi, right? Do you see 3 pi?
Yeah, so it would be -4.
-4. Okay, good. Okay, everyone? If you have F with a number inside of it, you're going into the graph and you're trying to read it and trying to figure out what's the Y coordinate there, right? Now, the next question is, what is the domain of the function? What's the domain? And here's the way I think about domain, all right? When I have a graph, here's kind of the way I look at it. I say to myself, you know, when I'm looking at this graph, right? I'm looking at that graph in yellow. I'm kind of trying to figure out what X values correspond to the graph. So if I look on the X-axis between here and here in that yellow region, in that green region, if I pick any value of X in here, any value, I will have some point on the graph that corresponds to that value, right? No matter what X I pick, where I am on the X-axis there, I'm always going to have some output. And that happens between here, this left end 0, and it stops right here. And that looks like it's right there at that point. That happens at 4 pi. So I've got graph between 0 and 4 pi. Do y'all see that? Between 0 and 4 pi, if you look up or down, you're going to see graph. So my domain here would be 0 to 4 pi. And I would include the 2 endpoints because at 0, I actually have a point, and at 4 pi, I have a point. I hope that makes sense. I'll say it one more time. I'm looking on the X-axis, and I'm saying, look up and down and make sure you're hitting graph. And in this entire region, I'm hitting graph the whole time. Once I go past 4 pi, this is 4 pi. Once I go past 4 pi, I no longer have graph above or below. And if I go to the left of 0, I no longer have graph. So my domain is just between 0 and 4 pi. Now, range is the opposite of that. Instead of looking on the x-axis and looking up and down, you go to the y-axis. You go to the y-axis and you look left or right. And I hope that you see that here to here, if you look left and right, you've got graph in there. But it only happens between the lowest y value we ever get is -4, and the highest y value we ever get is +4. So all the outputs are between -4 to 4. So these are the outputs, these are the inputs. All your inputs have to be between 0 and 4 pi. All your outputs have to be between -4 and 4. Does that make sense or not? You know? If you want, you could say this is your x values, right? These are your x values. And then this is your y values. For D, what we're asking for D is all the intercepts. That's anywhere that our graph touches either the x or the y axis. So I'm going to just start with this point right here in red. This point is our y-intercept, because that's where our graph hits the y-axis. It's the 0.04. And then I have x-intercepts. I actually have a few of them. Those are here, 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 here. There's actually 4 of them. And all of them have the same condition that the y coordinate is 0 at all of those points. So all I do is list them all out. Pi over 2, 0. 3 pi over 2, 0. 5 pi over 2, 0. 7 pi over 2, 0. So I have 1 y-intercept. I have 4 x-intercepts. Questions? I'm gonna leave that there. I'm gonna move this down here to continue. For part E, how many times does the line y = 2 intersect the graph? Well, y = 2, you need to know is a horizontal line that goes through 2. So if I draw a horizontal line that goes through the value 2, I can see that I intersect 1, 2, 3, 4 times. So that's the answer. Let's look at the next one. Are there any questions on that one? Part F, for what values of x does the function spit out -4? Well, how many places do we get a -4 out? Only happens in 2 places, right? Here at these 2 bottom points, those are the only points where our y value is -4. So what are the 2 x values that give us that? Pi and 3 pi, right? Those are the inputs that I would have to do to get the output of -4. So I get pi here and 3 pi. One more. For what values of x is the function bigger than 0? What does that mean? Function bigger than 0. That means where's the function what? Where are the outputs? We want our outputs to be, say again?
They're above the x-intercept?
Above the x-axis, right? So we're trying to figure out where's our graph above the x-axis? Well, here right? In red there, it's above the x-axis. Here, actually all in that little region, our graph is above the x-axis. And here, our graph is above the x-axis, right? Those are like the three little regions where our graph is above the x-axis. And it wants to know the x values, right? The x values where it's happening. So if I'm between here and here, I've got positive values coming out. If I'm between here and here, my graph is above the x-axis. And if I'm between here and here, my graph is above the x-axis. So I need to list that out. Those green regions, I need to list them, and I need to do it in interval notation. So this first region here is everything from 0 to pi over 2. This region here is everything between 3 pi over 2 to 5 pi over 2. And then this last region is 7 pi over 2 to 4 pi. Just keep in mind, these are x values. I'm looking at this green, it's like a domain. I'm trying to almost like find a domain, but only where the graph is above the x-axis. So anything between here and here, between here and here, and between here and here, I get graph above the x-axis. Can somebody tell me why I put a bracket on 0, but a parenthesis on pi over 2?
Is it because the circle is closed?
Okay, so at 0, right? If I plug in 0, I get 4, right? So that's a positive number. So I'm above the x-axis. What about at pi over 2, though? At pi over 2, what's the value of the function?
Negative.
So you wouldn't.
Below.
Well, at pi over 2, isn't that an x-intercept? Isn't the value of the function 0 there? Is
Yeah.
0 positive? No. So I do not want to include pi over 2 because it's only between 0 and pi over 2, but right up to pi over 2, not actually pi over 2 itself. For the same reason, when I get to 3 pi over 2 and 5 pi over 2, that's between these two x values, I don't include 3 pi over 2 and 5 pi over 2 because that's where my x-intercepts are. And then this last one, 7 pi over 2, I don't include that because that's my x-intercept, but at 4 pi, I'm up at the top, so I do include that. This is a little bit of a tricky problem. You're going to probably have to do a couple of these. If you're confused, you're going to have to do a couple of these to try and catch on to it. Let me see. I want to look to see what else we have before. Yeah, let me just cover, I want to cover this last topic. It's very, very brief, and I think it's pretty easy. When it comes to functions, we have this concept called symmetry, the symmetry of functions. And when it comes to symmetry, there's 3 types of symmetry. Now, not every function has to have symmetry, right? So if somebody gives you a function, just generally speaking, it doesn't have to have any sort of symmetry. But if it does have symmetry, it's one of 3 types. The first type is called, you know what, I need to change something. Just put symmetry up here, not symmetry of functions, just put symmetry. Because this first one's not a function, fails a vertical line test, okay? So just symmetry in general. So if somebody gives you a graph, you can not have symmetry, or you can have symmetry, and it would be one of these 3 types. So the first type is called x-axis symmetry. And the way it works is, I think, pretty simple for people to understand. If you just look at the x-axis, you can see that the graph is a reflection of itself over the x-axis. So if I reflected this over, like almost like rotated it 3-dimensionally around that axis, that graph would land right on top of itself. So it's a mirror image of itself over the x-axis. That's called x-axis symmetry. Y-axis symmetry is the same thing except y-axis. So you go here, and if you were to reflect this over, right, or reflect that over here, they would land right on top of each other. Mirror image. That's called y-axis symmetry. Most students understand those two because it's like a mirror image. Origin symmetry is a little weird, okay? So what you do to see origin symmetry is you take like one part of the graph. Let's just say this red piece right here. Take that piece. But what I want you to do is see what happens if you do a double symmetry. You do a y-axis followed by x-axis. So if I were to take this and rotate this around the y-axis first, wouldn't it come out like this? That would be what it looks like if I reflected that red piece over the y-axis, yes? Now, reflect that dotted one over the x-axis. If you reflect that dotted one over the x-axis, you're going to land right here. And that's what makes origin symmetry. It's like a double reflection. And you could have also done it for the black piece. You could have taken the black piece, reflected it over the y-axis, it would have landed here, and then reflected it over the x-axis, and it would have come up and it would have landed on the red one. So when you have that happening, that's called origin symmetry. Those are the three types of symmetry you can have in a relationship, in a graph. Okay, I think let's see how the homework goes. I think there may be some problems you have an issue with. Do your best on you know what's there. If you get hung up on something, you know, come to my office hours, or you know, next class, beginning of class, you can ask questions. Anything you can't figure out on your homework, just skip it, move on to the next problem. And you know, if you get a couple of points taken off because you didn't do a problem, so be it. All right, that means you need some help with that. All right, I think we got a couple of minutes left, but we'll just wrap it up here. I don't think there's anything else that have time to cover. So everyone hopefully understands the expectations, do as much as you can of this homework, right? And we'll be back next week. Have a good weekend. I'll hang out for a minute if you have any questions.
Thank you, Professor.
Yep. Especially if you have any questions over anything I did here. If I need to clarify anything, just hang out and ask.
Thank you, Professor. Have a good one.
You too.
Have a good one, sir.
I do have a question.
Okay.
So earlier we were doing one, right? And it's like f of x is equal to, it's like radical 3x plus 12 over x minus 5.
Yes, the domain.
Yes. And then we started, like, you did it where it's like 3x plus 12 and then is greater than or equal to 0. And then we just completely, yeah. We like, how do you know? No, I don't even know like what my question is. It's like, why did we get rid of the radical? Or like, how do you know we're getting rid of it?
Yeah, we're not really getting rid of the radical. What we're doing is this. We're saying, let me just do a new page. So all we're saying is this. If you give me the square root, okay, it doesn't matter what's in here, okay? We actually have a name for this. It's called the radicand. That's what we call this thing. Whatever's underneath this radical symbol is called the radicand. What we know is that if this is a square root or a fourth root or a sixth root, we know that whatever's here cannot be negative, right? This cannot be negative or we're in trouble. I'm sorry, cannot be less than zero, right? If this thing is a negative number, we're in trouble. So then if it can't be negative, then we just have to ask ourselves one simple question. When is that bigger than or equal to 0? Right? So it's not like I'm getting rid of the radical. It's I'm just using the fact that I'm just really need to make sure that whatever it is, it stays positive or 0.
Okay.
Make sense? So we
Yes.
took this and we said, oh, here's the radicand. We need to make sure it's not negative. Okay, that means make sure it's bigger than or equal to 0. All right, what makes it bigger than or equal to 0? Oh, as long as x is bigger than or equal to -4, boom, we're in business.
Got it.
Okay.
Yes. Alrighty. Okay, that was my question.
Okay, good question.
Alrighty. Thank you
Have
so
a good
much.
one.
I'll see you
All right.
Monday.
Yep.